of you. This is Sailaja, Department of Chemistry, K.B.N College, Vijayawada. Today I will discuss about the molecular representation. Okay. The organic molecules can be represented by the four different ways. First one is the wedge representation, second one is the Fisher representation, third one Newman representation, and fourth one is the Sahas representation. Okay. In wedge representation or dash notation is used to represent the three-dimensional structure of the molecules by using the two-dimensional surface like a sheet of paper or a computer screen. In this representation, there are three types of bonds are present. One line is the solid lines, and second one is the dashed lines, and third one is the wedge-shaped lines. Here, the solid lines represents the bonds that are in the plane of the paper, and the dashed lines represents the bonds that are extended away from the viewer. And for last one is the third one, wedge-shaped lines represents the bonds oriented facing the viewer. And next one, Fisher projection. In Fisher projection representation, the backbone of the atoms, carbon chains are represented simply by a straight line. Here, the example is the 2-bromo-3-chlorobutane. Here, the carbon chain represented as a straight line, and the terminal functional groups are placed here. Here, this methyl group is placed here, and this methyl group is placed here. And the atoms or groups bonded to the chain carbons that are attached with the perpendicular lines. The atoms that are presented on that carbon represented as in perpendicular lines. Third one is the Newman projection formula. In Newman projection formula, carbon-carbon bond is represented by a first one, the dotted carbon is represented as a fronted carbon, and the back this is represented as a back carbon. The atoms groups are presented on a front or back carbon can be represented like this, Y or inverse or Y. And next, Sahas representation. Sahas representation resembles with the Newman projection formula. Here, the carbon-carbon bond is present. In Newman projection formula, the carbon-carbon bond is absent. In Sahas projection formula, the groups connected to the bond, both of front and back carbons drawn sticks and shows the bond angle of 120. Stereoisomers. We know that isomers have the same molecular formula, but the structural representation is different. In stereoisomers, isomers are the molecules that have the same molecular formula but have a different arrangements of the atoms in space. Stereochemistry. Chemistry that studies the properties of the stereoisomers, that is said to be stereochemistry. Stereoisomers can be classified into two types. First one is the conformational isomers, second one is the configurational isomers. In conformational isomers, the CC rotation is possible. In configurational isomers, the CC rotation is not possible. Example for the configurational isomers are the geometrical and optical isomers. Optical isomerism. The stereoisomers which differ only in the rotation of the plane polarizer light, that is said to be optical isomers, and the phenomenon is known as the optical isomerism. Optical activity can be introduced by the Dept in 1815. This is the plane polarizer light. This is the non-polarizer light. This non-polarizer light can be passed by a slit by using the glass slides. Polarimeter is an instrument that is used to measure the optical activity, is known as the polarimetry. And next, dextrorotatory and levorotatory. When the plane polarizer light turns the compound right side, that is said to be dextrorotatory. The compounds are said to be dextrorotatory compounds. And if the plane polarizer light turns towards to the left side, that is said to be levorotatory. Dextrorotatory can be represented by plus or small d, and levorotatory can be represented by the minus or small l. Next, chiral center or stereo center. An sp3 hybridized carbon with four different groups or atoms is known as the chiral center or asymmetric center or stereo center. This is the carbon contains chlorine, methyl and propyl and hydrogen. This sp3 hybridized carbon is said to be chiral carbon or asymmetric center carbon or stereo center carbon. In this compound is achiral due to because of here this carbon is bonded with the here methyl group and here also methyl group. So that is said to be achiral. Chiral molecules. The molecules which are not superimposables on their mirror images are called the chiral molecules. The chiral molecules are optically active. The molecules becomes chiral when it does not possess plane of symmetry, center of symmetry, as well as the alternative axis of symmetry. Achiral. These are said to be superimposable on their mirror images. These are the not achiral. And next, enantiomers. Enantiomers are the isomers that are the non-superimposable mirror images of each other, that are said to be enantiomers. Diastereomers. Diastereomers are the isomers that are not mirror images of each other. Here in this example, this is the mirror image of this. So 1 and 2 are said to be enantiomers and 3, 4 are said to be diastereomers. 1, 3 also diastereomers and 1, 4 also diastereomers. Enantiomers are the non-superimposable mirror images. Diastereomers are the not a mirror images of each other, that are said to be, that is the difference between the enantiomers and diastereomers. And next, optical isomerism in glyceraldehyde. The simplest aldose glyceraldehyde contains a one chiral center. This is the chiral center. Already we know that the chiral center that contains the carbon which undergo sp3 hybridized and attached with 4 different groups are said to be chiral center or stereo center. Okay, here in simple example glyceraldehyde, here hydroxyl group is present, here alcohol group is present, here aldehyde group is present, here hydrogen is present. So it is the chiral carbon. The simplest aldose glyceraldehyde contains one chiral center and therefore has 2 different optical isomers or enantiomers are possible. One of these 2 isomers designated as a plus isomer and another one is represented as a minus isomer or can be represented by plus capital D and small l. Here the OH group is present on the right side, so it is represented as a D-glyceraldehyde. In here the OH group present on the left side, so it is can be said to be L-glyceraldehyde. In D isomer the OH group on the right side and the hydrogen atom on the left side, whereas in L isomers the OH group on the left side and the hydrogen on the right side. The equimolar mixture of D-glyceraldehyde and L-glyceraldehyde forms a racemic mixture, and that racemic form is optically inactive due to the external compensation. Next one, optical isomerism in lactic acid. This is the simple D-lactic acid and this is the L-lactic acid. In D-lactic acid, this is the chiral carbon. In L-lactic acid, this is the chiral carbon. In chiral carbon, 4 different groups are attached, so it is a chiral center. In D-lactic acid, the OH group on right side and the hydrogen on left side. Here, the OH group in L-lactic acid, the OH group on left side and the hydrogen on the right side. The equimolar mixture of both D and L-lactic acid is optically inactive. In lactic acid, CH3, CHOH, COOH and the second carbon is a chiral. Already we saw that this is the second carbon, this is chiral center. And next, there are 2 optical active isomers are present in lactic acid. One is represented as a D and another one is represented as a L. D-lactic acid and L-lactic acid. Dextrorotatory lactic acid may be obtained from the meat extract is known as the sarcolactic acid. Dextrorotatory lactic acid can be isolated from meat, that is known as the sarcolactic acid. Levorotatory lactic acid may be obtained from the fermentation of the sucrose by bacillus. This is the microorganism that is in the acidic form. SD-levolactic, that is said to be SD-levolactic. And next, in addition to these optically active forms, there is a optically inactive form which results when dextro and levo forms are present in equal quantity. When equal mixture of D and L forms, that is called the racemic mixture, and racemic mixture is optically inactive. In racemic mixture is optically inactive due to the external compensation. The process of conversion of an enantiomer into a racemic mixture is known as the racemization. The process of conversion of enantiomers into the racemic mixture is known as the racemization. Ordinary lactic acid in sour milk or manufactured by the fermentation or by synthetic method is a racemic mixture. Ordinary lactic acid is present in the milk.